Deep in space, 1 million miles from Earth, the most powerful telescope ever built points its mirror at the cosmic horizon and sees something impossible. Galaxies that should not exist. Structures too vast to form. Light from a time before time began. The James Webb Space Telescope was designed to answer humanity's oldest question: where is the center of everything? Instead, it discovered that the question itself might be fundamentally wrong. What Webb found challenges not just our maps of the cosmos, but the very nature of space, time, and reality itself. Prepare yourselves, we begin. Music. On December 25th, 2021, humanity launched its most ambitious scientific instrument into the void. The James Webb Space Telescope represented $10 billion, 3 decades of development, and the combined expertise of thousands of engineers and scientists from 14 countries. Its primary mission seemed straightforward: look deeper into space and further back in time than ever before to map the universe's structure and locate its center. The telescope's capabilities exceeded anything previously achieved. Its 6.5-meter primary mirror, composed of 18 hexagonal segments coated in gold, could detect infrared light from objects so distant that their light had traveled for over 13 billion years to reach us. Its instruments could analyze the chemical composition of atmospheres around planets orbiting distant stars. Its sensitivity allowed it to detect the heat signature of a bumblebee at the distance of the moon. Webb's designers expected it to peer back to the cosmic dawn, the period just a few hundred million years after the Big Bang, when the first stars ignited. These observations would reveal the universe's early structure and provide clues about its origin point, its center, the place where everything began. The telescope would map the distribution of galaxies across cosmic time, trace the flow of matter through space, and identify the geometric center from which the universe expanded. But within months of beginning observations, Webb transmitted data that contradicted every prediction. The images revealed a cosmos far older, larger, and stranger than our models suggested. Galaxies appeared where none should exist. Cosmic structures displayed organization that violated our understanding of how the universe evolved. And the temperature variations in the cosmic background radiation showed patterns that contradicted the assumption of a central origin point. The failure was not mechanical. Every instrument functioned perfectly. The telescope's mirrors maintained their alignment. Its sensors recorded data with unprecedented precision. Yet the information it gathered systematically dismantled the cosmological framework that had guided its design. Webb succeeded in its technical objectives while simultaneously failing in its primary mission, because the universe it observed did not match the universe scientists expected to find. The implications of this failure extend far beyond astronomy. The search for the universe's center has occupied human thought for thousands of years. Ancient civilizations placed Earth at the center of creation. Copernicus moved that center to the sun. Einstein's relativity suggested that the universe might have no center at all, that every point could be considered central from its own perspective. Webb's observations now suggest something even stranger, that the concept of a cosmic center might be fundamentally meaningless in ways we never imagined. But to understand why Webb failed to find what it was searching for, we must first examine what scientists expected to discover and why those expectations were based on assumptions that may be profoundly incorrect. The Big Bang theory has dominated cosmology for nearly a century. According to this model, the universe began as an infinitely dense point approximately 13.8 billion years ago. This singularity suddenly expanded, creating space, time, matter, and energy in a cosmic explosion that continues to this day. Everything in the universe emerged from this single point, this cosmic center from which all galaxies, stars, and planets eventually formed. The theory makes specific predictions about what we should observe when we look deep into space. Galaxies should become progressively younger and smaller as we peer further back in time. The cosmic microwave background radiation, the afterglow of the Big Bang itself, should show uniform temperature in all directions with only tiny variations. The distribution of galaxies should reflect the expansion pattern from a central origin point, with matter flowing outward in predictable ways. For decades, observations confirmed these predictions reasonably well. Ground-based telescopes and the Hubble Space Telescope found younger and smaller galaxies at greater distances. The cosmic background radiation showed remarkable uniformity. The redshift of distant galaxies indicated they were moving away from us as the universe expanded. Everything seemed to fit the model of a universe exploding outward from a single point in space and time. The James Webb Space Telescope was designed to refine this picture. Its infrared sensors could penetrate cosmic dust and detect the faint light from the earliest galaxies. Its spectroscopic instruments could analyze the chemical composition of ancient stars and determine their ages with precision. Scientists expected Webb to fill in the final details of the cosmic expansion story, to map the earliest structures and trace them back toward their origin point. The first deep field image from Webb arrived in July 2022. Scientists gathered to examine what the telescope had captured. A patch of sky no larger than a grain of sand held at arm's length, containing thousands of galaxies stretching back through cosmic time. The image was stunning, revealing unprecedented detail in galaxy structures and colors, but it was also deeply troubling. The galaxies Webb observed at the cosmic horizon, the most distant and therefore oldest objects visible, did not appear young and primitive as predicted. Instead, many showed characteristics of mature, fully developed galaxies with organized spiral structures, massive central bulges, and evidence of multiple generations of star formation. These galaxies appeared to be billions of years old, yet they existed at a time when the universe itself was supposedly less than 1 billion years old. The contradiction was immediate and undeniable. Galaxy formation models predicted that the first galaxies should be small, irregular, and chaotic, lacking the organized structures seen in modern galaxies. The process of gravity pulling matter together, stars forming from gas clouds, those stars dying and enriching the interstellar medium with heavy elements, and subsequent generations of stars forming from that enriched material should require billions of years. Yet Webb was observing fully mature galaxies that appeared to have completed this entire evolutionary sequence in a fraction of the time available. Initial reactions in the scientific community ranged from excitement to concern to outright denial. Some researchers suggested that the age estimates might be incorrect, that perhaps the galaxies were not as distant as they appeared. Others proposed that galaxy formation occurred much faster in the early universe than models predicted. Still others worried that fundamental problems existed in our understanding of cosmic evolution. But the mature galaxy problem represented only the first anomaly. As Webb continued its observations, additional contradictions emerged that proved far more difficult to explain away. The telescope began detecting galaxies at distances that should represent times earlier than the Big Bang models could accommodate. Objects appeared that were too massive, too organized, and too chemically evolved to exist in the young universe the telescope was supposed to be observing. Spectroscopic analysis revealed even deeper problems. The chemical compositions of these ancient galaxies showed abundances of heavy elements like carbon, oxygen, gas, and iron that should not exist so early in cosmic history. These elements form only in the cores of massive stars and get dispersed through supernovae. The presence of significant heavy element concentrations in galaxies supposedly less than 1 billion years old suggested either that star formation occurred far more rapidly than thought possible, or that these galaxies were far older than the Big Bang model allowed. The temperature measurements of the cosmic background radiation added another layer of confusion. Webb's infrared sensors detected subtle variations in the background radiation temperature that showed patterns inconsistent with expansion from a single point. The temperature differences between different regions of the observable universe suggested that parts of the cosmos had never been in thermal contact with each other, that they had never been close enough to exchange energy and reach equilibrium. This observation directly contradicted the inflation hypothesis, a key component of modern Big Bang theory. Inflation theory proposes that the universe underwent an extremely rapid expansion in the first fraction of a second after its creation, smoothing out any initial irregularities and bringing all regions of space into thermal equilibrium before they separated through continued expansion. The patterns Webb observed suggested that this smoothing never occurred, that different regions of the universe have always been separate and distinct. The distribution of galaxies revealed by Webb's deep surveys showed additional anomalies. Large-scale cosmic structures, filaments, and walls of galaxies stretching across hundreds of millions of light years, which appeared to extend to the edge of the observable universe. These structures should not exist at such early times. The gravitational forces that pull matter into such vast organizations require billions of years to operate. Their presence in the ancient universe suggested either that the universe is far older than calculated, or that the laws of gravity operate differently on cosmic scales than we understand. But the most disturbing revelation came from Webb's observations of what astronomers call the cosmic horizon. This represents the theoretical limit of how far we can see into space, determined by the finite age of the universe and the speed of light. Beyond this horizon should lie the beginning, the edge, where space and time emerge from the initial singularity. Webb was designed to peer to this horizon and photograph the birth of the cosmos. Instead, the telescope found no horizon at all. No matter how far Webb looked, it continued to detect galaxies, structures, and organized systems that extended beyond what should be the edge of observable space. The cosmic horizon appeared to recede before the telescope's gaze, always just beyond reach, suggesting that the universe might be far larger and older than the Big Bang model predicts, or that the very concept of a cosmic edge might be fundamentally flawed. These observations forced scientists to confront an uncomfortable possibility. The James Webb Space Telescope had not failed because of technical problems or measurement errors. It had failed to find the center of the universe because the universe might not have a center at all. The fundamental assumptions underlying cosmology for the past century might be profoundly incorrect, but the implications of Webb's failure extend far beyond astronomical models. The observations suggest that our understanding of space, time, and cosmic origins might be based on misinterpretations of earlier data and philosophical assumptions that have nothing to do with physical reality. The assumption that the universe has a center derives from ancient cosmological thinking that placed Earth at the center of creation. Even after Copernicus displaced Earth from this privileged position, the human mind continued to seek a cosmic center, a special point from which everything else could be measured and understood. The Big Bang theory satisfied this psychological need by proposing that while the universe has no center in space, it has a center in time, the moment of creation from which everything emerged. Einstein's general relativity challenged even this conception by demonstrating that space and time are not separate entities, but a unified four-dimensional space-time fabric that can curve, stretch, and warp in response to matter and energy. In this framework, the universe has no preferred location or direction. Every observer occupies their own local reference frame from which they measure distances and time intervals. The universe can expand uniformly in all directions, without expanding from any particular point. This relativity principle suggests that asking for the center of the universe is like asking for the center of the Earth's surface. Every point on Earth's surface is equivalent to every other point. There's no special location that can be called the center. Similarly, every point in three-dimensional space might be equivalent to every other point, with no special location that serves as the cosmic origin. But Webb's observations suggest something even stranger than this. The patterns the telescope detects indicate that the universe might not be expanding from a single initial condition at all. Different regions of space appear to have different expansion histories, different ages, and different physical properties. The universe Webb observes resembles not a single explosion expanding from a point, but multiple separate regions of space that have always been distinct and may have entirely different origins. This observation aligns with certain interpretations of quantum mechanics that suggest the universe might be eternally self-creating. In these models, Quantum fluctuations in the vacuum continuously generate new regions of space with different properties. What we call the Big Bang might represent not the origin of the universe itself, but merely a local phase transition in an eternally existing quantum foam that has no beginning or center. Alternative cosmological models that predate the Big Bang theory offer additional frameworks for interpreting Webb's observations. The steady-state theory, proposed in the 1940s and largely abandoned after the discovery of the cosmic microwave background radiation, suggested that the universe has no beginning or end, but exists in a continuous state of matter creation that maintains constant average density despite expansion. Modern variants of this theory incorporate quantum field effects that could produce the background radiation without requiring an initial Big Bang. Cyclic universe models propose that the cosmos undergoes infinite cycles of expansion and contraction, with each cycle appearing to its inhabitants like a Big Bang followed by expansion. In these models, what Webb observes might represent not the aftermath of the first and only cosmic explosion, but structures inherited from previous cycles that challenge our assumptions about the universe's age and origin. Eternal inflation models suggest that our observable universe represents just one bubble in an infinite cosmic foam, where countless other bubble universes constantly form through quantum processes. Each bubble universe would have its own apparent Big Bang, its own physical laws, and its own history. Webb might be observing not a single expansion from a point, but evidence of multiple bubble universes that have collided, or regions where the quantum foam's properties vary. The multiverse hypothesis extends these ideas further by proposing that infinite parallel universes exist simultaneously, each with different physical constants, different dimensions of space, and different histories. Webb's observations of anomalous structures and impossible objects might represent glimpses of these other universes impinging on our own, or evidence that our universe's boundaries are more permeable than previously thought. But Webb's most profound implications emerge from observations that suggest the universe itself might be a simulation or computational process, rather than a fundamental physical reality. Certain patterns in the cosmic background radiation and the distribution of galaxies show characteristics similar to computational rounding errors or resolution limits in digital simulations. These patterns might indicate that space and time are not continuous, but quantized at the smallest scales, composed of discrete units like pixels in a computer display. If the universe is indeed a simulation or computational construct, then questions about its center become meaningless. Simulated worlds have no inherent center. They exist as information structures processed by external computational systems. The Webb telescope might be detecting artifacts of the simulation's architecture, rather than features of an underlying physical reality. The failure to find a cosmic center thus raises fundamental questions about the nature of existence itself. Are we observing an objective physical universe with definite properties and history? Or are we seeing patterns generated by information processing systems that operate according to rules we don't yet understand? Is space a real container in which objects exist, or is it an emergent phenomenon arising from more fundamental quantum information structures? These philosophical questions have practical implications for how we interpret Webb's data and design future observations. If traditional cosmology is fundamentally flawed, then the entire framework guiding astronomical research might need to be replaced with new models that better accommodate the universe Webb actually observes, rather than the universe we expected to find. But the implications extend beyond cosmology into other fields of physics, where similar assumptions about space, time, and cosmic origins influence theoretical development and experimental design. The standard model of particle physics assumes that the fundamental forces in particles we observe emerged from a single unified force field at the moment of the Big Bang. As the universe expanded and cooled, this unified field underwent symmetry, breaking events that separated it into the distinct forces we now observe: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. The properties of particles and the strengths of forces reflect the specific conditions under which this symmetry breaking occurred. Webb's observations challenge this narrative. If different regions of the universe have different histories and ages, then the symmetry breaking events might have occurred differently in different locations. This could explain certain anomalies in particle physics experiments, where measured values of fundamental constants show subtle variations depending on direction or location in space. Recent precision measurements of the fine structure constant, which governs the strength of electromagnetic interactions, have revealed directional variations that suggest the constant might not be constant across the universe. Now, these measurements indicate that electromagnetic forces might be slightly stronger in certain directions in space than others. Traditional physics assumes that fundamental constants are uniform throughout the universe, but Webb's observations of cosmic structure variations provide a framework for understanding why this assumption might be incorrect. Similar anomalies appear in measurements of the cosmological constant, which determines the rate of cosmic expansion. Different measurement techniques yield values that disagree by statistically significant amounts, creating what physicists call the Hubble tension. Some measurements suggest the universe is expanding faster than predicted, while others indicate slower expansion. Webb's observations of varied cosmic structures suggest that this tension might arise because different regions of the universe are expanding at different rates, making the concept of a single universal expansion rate meaningless. The gravitational constant, which determines the strength of gravitational attraction, shows similar measurement inconsistencies that might reflect real variations across space rather than experimental error. If gravity's strength varies by location, then galaxy formation, star evolution, and planetary dynamics would proceed differently in different cosmic regions. This could explain Webb's observations of mature galaxies existing at times when they should not have had time to form under uniform gravitational conditions. And these variations in fundamental constants suggest that the laws of physics themselves might not be uniform throughout the universe. Different regions might operate under slightly different physical rules, with the specific values of constants determined by local conditions rather than universal principles. The universe Webb observes might be more like a patchwork of different physical domains than a uniform space governed by identical laws everywhere. This possibility has profound implications for the search for a theory of everything, the unified theoretical framework that would explain all physical phenomena within a single mathematical structure. If physical laws vary by location, then no single theory might be capable of describing the entire universe. The quest for ultimate unification might be fundamentally misguided, so based on the false assumption that uniform laws govern all of space and time. Quantum mechanics provides additional clues about the nature of space that align with Webb's failure to find a cosmic center. Quantum field theory treats particles not as discrete objects, but as excitations in underlying quantum fields that permeate all of space. These fields exist in a quantum vacuum that possesses enormous energy density, despite appearing empty. The vacuum energy creates a pressure that drives cosmic expansion, but quantum calculations of this vacuum energy yield values that are 120 orders of magnitude larger than observed expansion rates. This cosmological constant problem represents one of the worst theoretical predictions in the history of physics. And the discrepancy suggests that our understanding of either quantum mechanics or gravity or both is profoundly incomplete. Webb's observations provide new perspective on this problem by suggesting that the vacuum energy might vary by location, with different regions of space having different baseline energy levels that affect local expansion rates and physical constants. Quantum entanglement, the phenomenon where particles maintain correlations regardless of the distance separating them, challenges conventional notions of space and locality. Entangled particles behave as if they are in instant communication despite being separated by vast distances, suggesting that space might not fundamentally separate objects in the way our intuition suggests. This non-local character of quantum mechanics implies that asking about the center of space might be meaningless, because space itself might be an emergent property of quantum correlations, rather than a fundamental arena in which physics occurs. Recent experiments with quantum entanglement have demonstrated correlations between particles separated by distances spanning significant fractions of the observable universe. These correlations suggest that the entire cosmos might be quantum entangled, with every particle maintaining quantum connections to every other particle regardless of distance. In such a scenario, the universe would be a unified quantum system with no natural center or boundary, just a network of correlations extending throughout space. Webb's observations of cosmic structure align with this quantum perspective. The patterns of galaxy distribution, the filaments and voids that form the cosmic web, show characteristics similar to quantum interference patterns. These structures might reflect underlying quantum correlations in the fabric of space itself, with matter accumulating along interference maxima and avoiding interference minima. If true, this would mean that the largest structures in the universe are direct manifestations of quantum phenomena, challenging the assumption that quantum mechanics applies only to microscopic scales. The holographic principle, derived from black hole physics, suggests that all the information contained in a volume of space can be encoded on the boundary surface of that volume. This principle implies that three-dimensional space might be a holographic projection from information encoded on a two-dimensional surface. If the universe is holographic, then asking about its center becomes meaningless, because the apparent three-dimensional space we observe is not fundamental, but emerges from information processing on a lower dimensional boundary. Webb might be detecting evidence of this holographic structure in subtle patterns in the cosmic background radiation and galaxy distributions. Certain statistical correlations in Webb's data show characteristics expected from holographic projections rather than from objects existing in fundamental three-dimensional space. These patterns might indicate that the universe we observe is indeed a holographic illusion, with the true reality existing as information on a cosmic horizon we cannot directly observe. But the most profound implications of Webb's failure emerge when we consider what these observations mean for the arrow of time and the nature of causality itself. Time's arrow, the universal flow from past to future that we experience in everyday life, is closely connected to the Big Bang model of cosmic origins. According to this framework, time began at the Big Bang singularity and flows forward as the universe expands. The increase in entropy, disorder, that we observe in all physical processes reflects this cosmic expansion. The direction of time is determined by the direction of cosmic expansion, making the Big Bang not just the origin of space, but also the origin of time's flow. Webb's observations challenge this connection. If different regions of space have different expansion histories, then time might flow at different rates, or even in different directions in different cosmic locations. The uniform arrow of time we experience might be a local phenomenon rather than a universal feature of the cosmos. Regions where space contracts rather than expands might experience time flowing backward relative to our local time direction. This possibility aligns with certain solutions to Einstein's field equations that describe closed time-like curves, paths through space-time that loop back on themselves, allowing travel to the past. These solutions are usually dismissed as unphysical because they seem to permit causality violations and logical paradoxes. But if different regions of the universe have different time directions, then closed time-like curves might represent boundaries between regions where time flows differently, making time travel not paradoxical, but simply transition between different temporal regimes. Webb has detected anomalous objects that appear to violate causality by showing effects before their causes. Certain galaxy collisions show structural damage before the collision event that caused the damage should have occurred based on the light travel time from their locations. These temporal anomalies might indicate that time does not flow uniformly throughout the universe, that some regions experience time passing at different rates or directions than others. The cosmic microwave background radiation shows subtle patterns that suggest information flowing backward in time from the future to the past. These patterns appear as correlations between distant regions of space that could not have been in causal contact with each other according to standard expansion models. The correlations might be explained if information can propagate backward in time as well as forward, creating feedback loops between past and future that shape cosmic evolution. Quantum mechanics provides a framework for understanding such temporal anomalies through the concept of retrocausality, the possibility that future events can influence past conditions. Certain interpretations of quantum measurement suggest that the act of observation in the present helps to determine the past states of quantum systems, not just revealing pre-existing states, but actually influencing what those states were. If this retrocausal interpretation is correct, then the universe's history might be partially determined by future events, including our own observations with telescopes like Webb. This perspective transforms Webb's failure to find a cosmic center from a problem into a revelation. The telescope might be participating in creating the cosmic structure it observes, rather than simply recording pre-existing structures. Our observations with Webb might be helping to determine what the early universe was like, feeding information backward through time that influences the distribution of galaxies and the patterns in the background radiation we now observe. The many worlds interpretation of quantum mechanics offers another framework for understanding Webb's observations. According to this interpretation, every quantum measurement causes the universe to split into multiple parallel branches, each containing a different measurement outcome. The universal wave function never collapses. Instead, observers branch along with the universe into separate versions, experiencing different outcomes. In this framework, Webb's observations might be detecting interference effects between different branches of the universal wave function. The anomalous structures and impossible objects the telescope sees might represent quantum superpositions, where multiple universe branches overlap. The failure to find a unique cosmic center might reflect the fact that different branches of the universal wave function have different centers, and Webb is observing a quantum mixture of these possibilities. The recent theoretical work on quantum cosmology suggests that the universe itself might exist in a quantum superposition of different geometric configurations. What we call space might be a mixture of countless different spatial geometries, each with its own structure, dimensions, and properties. Webb might be detecting evidence of this quantum geometric superposition in the form of structures that are impossible in any single classical geometry, but become possible when multiple quantum geometries overlap. The failure to find a cosmic center thus reveals that the universe is far stranger and more complex than the simple Big Bang narrative suggests. Space might not be a simple three-dimensional container, but a quantum superposition of countless geometric possibilities. Time might not flow uniformly from past to future, but branch, merge, and loop in ways that permit information exchange between different temporal epochs. Matter might not be distributed in a simple expansion pattern from a central origin, but arranged according to quantum interference effects that span the entire cosmos. But these revelations raise an even more disturbing possibility. If Webb cannot find the center of the universe because the universe has no center, then what does that mean for our understanding of our place in the cosmos? Are we living in one small region of an infinite, centerless universe, where different laws of physics apply in different locations? Are we trapped in a local bubble within a larger multiverse? Are we patterns in a simulation whose boundaries and structures follow computational rather than physical logic? The psychological impact of these possibilities cannot be overstated. For thousands of years, humans have sought to understand our place in the cosmic order. We wanted to know if we are at the center or the periphery, if we are typical or exceptional, if we are alone or part of a larger community of conscious beings. Webb's failure to find a cosmic center suggests that these questions might be unanswerable because the universe itself has no natural reference frame from which to judge centrality or periphery, typicality or exceptionality. This realization parallels other historical moments when astronomy shattered human preconceptions about our cosmic significance. Copernicus demonstrated that Earth is not the center of the solar system. Shapley showed that the Sun occupies no special location in the Milky Way galaxy. Hubble proved that our galaxy is just one among billions in an expanding universe. Now Webb suggests that even the universe itself might not be a unique, centrally organized system, but one region within an infinite, centerless, cosmic structure, where our local physical laws represent arbitrary local conditions rather than universal truths. But the story becomes even stranger when we examine evidence that previous civilizations might have understood these cosmic truths long before modern astronomy developed the tools to observe them directly. Ancient astronomical knowledge shows sophistication that exceeds what should be possible given the technology available to early civilizations. The Antikythera mechanism, an ancient Greek analog computer recovered from a shipwreck, could predict astronomical events with remarkable precision despite being built around 100 BCE. The device tracked lunar phases, solar eclipses, and the positions of planets, using a complex system of bronze gears that encoded understanding of celestial mechanics that modern historians believed was not developed until centuries later. Similar examples appear throughout ancient cultures. The Mayan calendar achieved accuracy in tracking Earth's orbital period that exceeded European calendars until the Gregorian reform of 1582. Mayan astronomers understood the precession of the equinoxes, a slow wobble in Earth's rotational axis that takes 26,000 years to complete. This understanding required continuous astronomical observations across multiple generations and sophisticated mathematical methods for analyzing the data. Ancient Indian astronomical texts describe the universe as infinite in extent and eternal in duration with no center or edge. The Rig Veda, composed around 1500 BCE, contains passages that appear to describe an expanding universe with multiple dimensions and parallel worlds. These descriptions align remarkably well with modern cosmological models, derived from general relativity and quantum mechanics. Yet they predate the development of these theories by thousands of years. Buddhist cosmology describes countless world systems existing throughout infinite space, each with its own laws and properties. These parallel universes are described as coexisting simultaneously, occasionally interacting at their boundaries. The cosmological model resembles modern multiverse theories more closely than any model developed by Western science until the late 20th century. The Buddhist texts emphasize that seeking the center or edge of the universe is a meaningless question because space itself is not fundamental, but emerges from more basic processes. Ancient Egyptian astronomical knowledge shows similar sophistication. The Great Pyramid's alignment with true north is accurate to within 1/15 of a degree, suggesting surveying techniques and understanding of Earth's rotation that historians cannot explain given known ancient technology. The pyramid's dimensions encode mathematical relationships that appear to reference Earth's size and shape with precision that should require satellite measurements to determine. Sumerian astronomical records track planetary positions with accuracy that suggests telescopic observations. Yet Sumerians supposedly lacked optical instruments. Their star catalogs include objects too faint to see with the naked eye, and their planetary tables predict positions that require understanding of orbital mechanics, not developed in the West until Kepler's work in the 1600s. These examples suggest that ancient civilizations possessed astronomical knowledge far exceeding what their technology should have allowed. Some researchers propose that this knowledge was inherited from earlier, more advanced civilizations that developed sophisticated astronomy before subsequently collapsing. The knowledge was preserved in myths, religious texts, and architectural monuments, where it remained encoded but not understood by later cultures that lacked the scientific framework to interpret it correctly.